come to you tonight from my dining room wearing my sock monkey pajamas. They are onesies. So if you have questions that aren't about my sock monkey pajamas, feel free to ask. Hi, Jacinta. Cis-trans is when you're looking at ring structures or alkenes, carbon-carbon double bonds, and you're just looking to see if the orientation is pointing in the same direction, which would be considered cis, or if it's in opposite directions, which would be trans. So, for example, let me pull this up. If I have cyclohexane and I have two groups on it, doesn't matter what the two groups are, we'll call these the two methyl groups. You can see that they're both pointing straight up, so that means those are cis methyl groups to each other. So you could also identify groups as R and S if it's on a ring, but in the time being, all I'm asking is that you can look in something and tell whether it's cis or if it's trans. If you have a double bond, oops, let me get the regular bond back. Why is that not? Hold on a second, sorry. Hold on just a second. Hey Brandon, can you get that? Thank you. Okay. So for example, the molecule I just made, those groups are hanging on opposite sides of the carbon-carbon double bond, whereas if I had this structure, they would be on the same side of the carbon-carbon bond. And so that means, let's see, that this molecule here would be trans, and this molecule here would be cis. Does that make sense? It's essentially just identifying a relationship between two groups. Okay, good. Awesome. More questions? Explain R or S again. So, Diana, that's a really, really big question that, I mean, would take another hour to explain. Can you ask a more specific question about R and S stereochemistry? Hey, Duncan. It's not streaming. Well, it's obviously streaming. Can you guys see me? Andrew, yes, if you have more than one halogen, any kind of prefix that you have, you're going to have to alphabetize it. So if you have a bromine, an iodine, and a methyl group, you still have to alphabetize all of them. Jacinta, look at the 1,3 diaxial interaction section of your notes. If you have 1,3 diaxial interactions, those are causing too much steric strain, and those are going to be less stable than if you have fewer 1,3 diaxial interactions. See if I can do a really good chair on here. So axial, meaning in the axial position. 1,3, meaning carbons 1 and 3. And then those would interact with each other. Whereas if we had them in the equatorial position, and you can actually see this if you're using a model kit. If you had something in the equatorial position, like these two, they're not going to interact with each other. They're very far apart. Did you need something, Diana? So, Diana, if you're looking at stereoisomers with R and S, if they're mirror images of each other, then one would be R and one would be S, or if it has basically just the opposite. So you could have something with 3 chiral carbons like RRR, and the enantiomer would be SSS. Diastereomers are when you have a different mixture of those, or when you have cis-trans isomerism. So if you have one group that's, or one molecule that's cis, like, hold on a second. So let's look here. If I make this cyclohexane with 1,2-dimethyl on it, and the 1,2-dimethyl are pointing in the same direction. Okay, and then I have another cyclohexane, 1,2-dimethyl cyclohexane, and one of them's pointing in up and down directions. So this would be cis to each other, and the other would be trans, right? Cis being the one on the left and trans being on the right. And so that's cis-trans isomerism. Now you could look at these, and also we couldn't do it the ones I did because they have a plane of symmetry, but let's put like a nitrogen there so that they're not the same. Okay, so now we have 2 chiral carbons on there, and you could come up with the stereochemistry using the RRS system just like we've done with other things. If you have, say for example, let me pull this up. If you have something that has RR stereochemistry, then the enantiomer would be SS, right? If I had RR, a diastereomer, oops, would be RS or SR. So as long as it's not the mirror image, meaning the actual opposite of the stereochemistry, then you're going to be looking at enantiomers. I don't know if that answers your question, but you know, on the flip side, if I had an RS, what would the enantiomer be for RS? Anyone can answer. Anyone? Ah, that's my girl, is SR, okay? And so what is a diastereomer? Thank you, Andrew. What would be there are 2 diastereomers, what would they be? All I see is a bunch of sir. Yes, RR or SS, right? exactly. So either one of those would be correct if you were trying to do the diastereomers, which means if you had something with 2 chiral carbons, there's 4 possible stereoisomers, 2 sets of enantiomers, and then basically 2 sets of diastereomers. Did that answer your question? I'm having trouble figuring out exactly what you needed out of that. Hey, Brandon, could you give me some more water? Thank you, sir. Ah, awesome. Then that was a much easier question than what I was thinking of trying to re-explain all of stereochemistry. Thank you.
That's cool.
More questions? There's like a 10-second lag, so... Jacinta, it's not exactly the same because last time I taught this class, I covered different chapters. So I mean, it's still 4 pages, roughly broken up based off how much time we spent on specific topics. Rank 1 to 4 on the atomic weight, sure. So let me make this a little bit bigger. Sorry, it takes a while for me to draw things in here. If I didn't say equatorial or axial, it doesn't matter. You'll have 2 conformers, right, where there'll be one or the other, so just pick if I didn't ask. If I ask for lowest energy, then you would have to pick the ones where you reduce the number of 1,3 diaxial interactions. Okay, so Andrew, here I have some sort of 1, 2, 3 force substitute. So 2-fluorobutane, right? So what would we rank these as far as the priority groups go? Okay, so I think that's what you're asking, right? So number 4, we know that one would be hydrogen. What has the highest atomic weight? A CH2, or I'm sorry, a carbon, a fluorine, or a carbon? If you said the one that I just drew, I didn't work it out yet. Yes, that's us. Okay, so number 1 would be, oh shoot, that fluorine didn't go where I wanted it to. Yeah, you guys are all answering me, but it didn't go where I wanted it. There we go. Sorry about that. Okay, and then we have to basically look at our other 2 options. I have a carbon that is a CH3 over there on the left, and then I have a CH2CH3. So you have to go to the next highest atomic weight difference. So if you're looking at essentially, let me draw it this way. Okay. A carbon that has 3 hydrogens attached to it. And I'll just put that as a generic R group. And then I'm comparing that to this. An R group that has 2 carbons one of which has 2 hydrogens and the other which has 3. Okay. So what I have to look at first, and I don't know if I can highlight this. There we go. Hopefully you guys can see that. So I look at this CH2 and I'm like, okay, well, that's a carbon with 2 hydrogens attached to a carbon. This is a carbon attached to 3 hydrogens, no other carbon. So this would have to have the one on the, I don't think you guys can see my cursor, can you? The one on the right would have the higher priority using the Kahn-Ingold-Prelog rules, because when we look at the carbon, you have to look at what it's connected to, okay? Now, where that gets complicated is if you have something with double bonds or triple bonds. So if you have a double bond, you count that as 2 connected to the same thing instead of 3. So, or instead of just 1, sorry. So that would make this group over here, put it down here, that would be number 2. And that would be number 3. And as you said, that would be a stereochemistry. We can see that, let's see. Oh. I'm trying to like make an arrow here. It's not working. Swap. Ah, that got it. Okay. Diana, we talked about that in class, and it's in the book, so check it out. Kahn-Ingold-Prelog rules for priority of stereochemistry. You didn't do the reading. That's what we use to figure out which direction things are going. Let's see. Winter. Made it so I can do that as well. Sometimes it's easier to not use ChemSketch and to actually just draw things. With two axial groups, not 2 axial molecules, 2 axial chair conformation that are pointing up and down be more stable than 2 equatorial. Well, which one has fewer 1,3 diaxial interactions? So 2, we'll just call those fluorines. Oops. I'm going to turn my mic off here for just a second. Hold on. Sorry about that. Red's driving me crazy. I need my husband to come and get him. Okay. He wants to go outside. He keeps scratching at the door. All right. So if we count these 2 examples, how many 1,3 diaxial interactions are on this one here? That is the question. Right. So in the equatorial position, this one has 0 1,3 diaxial interactions. And then this one here would have, let's see, there's 2 hydrogens there. So that's 1, 2. And then there is a hydrogen here and a hydrogen here. So that's another one and another one. So this one has 4 1,3 diaxial interactions. This one here only has 0, so you would pick the ones that were in the equatorial position as a favored. Now, if I do something like this, where, oh, wait a second. Okay. Right, so it's less stable. So the 1,3 diaxial interactions are any group that can interact with hydrogen or another group, okay? So an example would be if I have an OH here and I have a bromine here, okay? Well, we don't have to worry about 1,3 diaxial interactions on top because those are all hydrogens and they're little tiny hydrogens and they don't interact with each other. Sorry, when I touch my screen, it makes my screen bounce around. So here, though, if I draw all 3 of the equatorial, all 3 of the axial coming down at the bottom, I have this interacting with the OH, I have the bromine interacting with the H, and I have the bromine interacting with the OH. Couldn't the first, there's no reaction going on here, Jacinta. I'm not sure what you're asking me. Hydrogens are too small to interact with each other sterically, so we don't count those. But this one down here would have 3 1,3 diaxial interactions. Now, if we switched that chair conformation to the other chair, okay, where now this point here is this point down there. Okay, so then I would have a bromine and then an OH. Okay, so now the bromine is going to be really bad about B, sorry. The bromine is going to be in the equatorial position. The OH is going to be in the equatorial position, and there will be no more 1,3 diaxial interactions. So this would be the most stable, once again, because it has 0 1,3 diaxial interactions, and this one has 3. Now, there's also I need like 8 screens of this. The possibility of having 2 that are equal in stability. So if I had something like this where I have one, let's put an OH up there and an OH down here. So if I do the chair flip, okay, where this point down here is now this point there. I'm circling it. That looks like an oxygen's there. I'm sorry if that's confusing. X marks the spot. I'll put an X there. So that's that same carbon, right? So if I count over 1, 2, 3, 4, 5, and 6, that number 3 position would be right here, and is now going to be axial. And the number 4 position is now going to be equatorial. So here I had a total of 2 1,3 diaxial interactions. And in this one at the bottom, I still have 2 1,3 diaxial interactions. So it's possible in some cases that you don't have necessarily a more stable conformation. It's entirely possible they can have the equivalent stability. And I wouldn't ask you what would be more stable between like an OH group or a BR or something like that. So you don't have to worry about getting into that level of detail. That would be a little bit out of the scope of this class for next semester. Hopefully that explains things. Jacinta, now that I'm looking at what I just drew, it looks like a complete mess. I'm hoping it made sense as I was talking about it. But please ask me some questions if you have them. (1,3) diaxial interactions do any group can interact with hydrogen or other groups. Hydrogens don't interact with themselves. So I did not consider that a 1,3 diaxial interaction. Okay. The first one. The first one here on top has two 1,3 diaxial interactions. Delcas. But so the 1,3 diaxial interactions have to do with just the hydrogens. It's just any kind of group that can basically sterically interfere through van der Waals interactions, any kind of other group on there. So if you have, just keep drawing cyclohexane chairs over and over again. They're getting a little bit better though. If I have one group here, I'll just call it group X, and a group here, that's group X. Group here, we'll call that X. And then this one here is a hydrogen. And this is a hydrogen. And this is a hydrogen. Okay. So what I want you guys to look at is how many 1,3 diaxial interactions are in the molecule I just drew. It would be easiest if you look at the top and then the bottom of the chair. Yeah, sorry. Jacinta, their axis, the axial positions, that's why they're called 1,3 diaxial interactions. So it's not something that we see in the equatorial position because equatorial positions are pointing out. Okay. Duncan's saying 5. Duncan, how many on top and how many on bottom? Let's see if I can change the color of this. I bet I can. Jacinta's going with 6. 3 on top, 2 on bottom. Okay, let's look. So can the X's interact with each other? Yes. So that's 1. The X and the hydrogen can interact. That's 2. And so can the other X. So here at the top we have 3. So if you said 3, then yes. Now here at the bottom, the hydrogen can interact with the X, whatever that group is, as long as it's not another hydrogen. So that's 1. The one here at the bottom can interact. That's 2. But the hydrogens can't interact because they're too small. Okay? So we don't count hydrogen-hydrogen interactions. That's why on regular cyclohexane we have 0 1,3 diaxial interactions just by itself. So there's 2 down here. 2 plus 3 equals 5. This is kind of fun. Okay. Does that make sense, Jacinta? I'm hoping that makes sense. Oh shoot, hold on. Sorry. I didn't mean to cuss at you guys. You want to try another one? Let's try another one. I have a feeling one day, when there's no more people on the earth or something, we're going to end up with all these YouTube videos, and mine aren't going to make a lick of sense to most people. Is that professor wearing PJs? Yes, she is. Okay. Let me pull that up. Okay. So let's do... Oh, shoot, sorry. I've drawn better chair conformations, but that'll work. Alright. Yeah, I'll do that one next, Andrew. So, tell me how many 1,3s we've got pointing up, and how many we have pointing down. 3 up, 3 down. All right, let's look. So bromine and hydrogen. Oh, let me do it better red so you can see a little better. There's 1. There's 2. There's 3. So if you said 3 on top, I agree with you. And then here at the bottom, we have OH to OH, that's 1. OH to H, that's 2. OH to H, that's 3. So there's another 3 on top. So if you said 3 on top and 3 on bottom to equal 6, you got it right. Diana's like, I changed my mind. There's 6. Okay, so, and if you want to really challenge yourself, take this molecule, flip it into the other boat, and, oh heck, we can do that. I don't know why I'm acting like we don't have this capability. We can flip the boat and see which one will be more stable. So let me go down here real quick. If you have epilepsy, then you might not want to stare at me going back and forth. Okay, so bromine, the tip is now down here. Did he just yelp? The OH would be right there. Sorry, the dogs just came in, so you might hear them clicking around. And let's see, another OH here. I had one more group, didn't I? CH3 there. Okay, so you'll notice here that, I mean, there's still something in the axial positions, they're just hydrogens now. And the hydrogens don't interact with each other because they're tiny little hydrogens. Hydrogens are tiny. Here we go. So there's 0 on top and 0 on bottom for a total of 0. So that's a good thing to kind of do. Let me see if I can scroll out so you guys can kind of see both. All right. Newman projection into a boat. What just happened up there? Just sound like my floor's caving in because Red jumped on something. I don't know if I've told you guys this. Red is a gigantic dog. Okay. So I can actually do Newman projections and stuff in ChemSketch, but this might actually be faster. So all right. So a Newman projection. Okay, let me answer Duncan really quick since this is the same thing. Different from diaxial interactions. When labeling, oh, it's different from diaxial interactions. Maybe molecule pairs, if the only difference is that groups were both outwards and are now both inwards. They're different conformers. So those are conformational isomers. So they can sometimes have 2 different energies, right, depending on the number of 1,3 diaxial interactions. But they are the same molecule, they're just conformers of the same molecule, or different energy states of the same molecule. Okay, so a Newman projection into a boat. Well, so Andrew, the first thing is that the only way you could do a Newman projection into a boat is if it is a Newman projection of cyclohexane. Okay, so that's first off, all right? So, you know, if we had just a regular Newman projection like this, we could not, and let's just put hydrogens as all these, we couldn't turn this into a boat form of cyclohexane because it's only got 2 carbons, right? It's only ethane. So we can't do that. Okay. Now that I've said my piece on that, so if we have both forms of cyclohexane, which is any cyclohexane, right? Well, that looks horrible. Fix that. And you'll notice with these, oh, they're basically always, I'm like running out of room. These are always going to be in a staggered conformation, okay, if we're looking at a boat. So let's, did I get everything right there? Kind of want to, that was a little confusing how I had that. Okay, so let's make it so that it looks like something other than just regular cyclohexane. Let's put a Br there and a Br there. So we're going to have a 1,2-dibromocyclohexane. I'll make these hydrogens. I know, I'm sorry, I'm running out of space on the side there. Okay. So what I think is the easiest way to tackle these, and I actually did this earlier today, I was showing how numbering can be really, really useful to, who was I talking to about that? Maybe that was yesterday. I think it was Janae. Yeah. So let's just number things, okay? So I usually start left to right. I don't know if that's because I'm left-handed or if just naturally we tend to read left to right, but this carbon here in the middle would be carbon number 1, right? The one behind it is carbon 2. Then the one connected to carbon 2 would be carbon 3. The one connected to carbon 3 would be carbon 4, which would be the other big round ball. 5 and 6, okay? So check. I've got all 6 carbons for cyclohexane, okay? Now, we can convert that to a chair. I really wish I would have made myself more room here. Okay. So if I call this one here carbon 1, what's coming off of it? A bromine. Is it pointing up or is it pointing down? It's pointing down. So I'll stick a bromine on there. Carbon number 2. Does it have a bromine on it? Yes. Is it pointing up or down? It's pointing up. So I'll put a bromine on there, pointing up. Okay. So this could flip, right? You can actually tell which ones of these are axial and which ones are equatorial. So this one, that one, and there would be a hydrogen down here and a hydrogen, well, 2 of them each actually. So there are 3 that I've circled in blue that are axial, and then 3 here at the bottom would also be axial. And then for equatorial, you can see those because they're the, oh no, what have I done? They're the ones that are hanging out on the periphery, and one of the ones there, okay? So that just looks like a big cluster mess of a bunch of circles around numbers and letters. Hopefully that answers your question. Did that answer your question, Andrew? Do we need to do another example? I'm used to working with a much larger board, obviously. Kinda. Do another one. Come on. Wrong one. Try that again. Oh! I misread your question and assumed that I answered exactly what you asked me. We haven't learned how to do boats. And I don't expect you to know how to do boats. And so tonight I'm not going to talk about doing boats. So that was definitely a chair confirmation because I assume that's what you were asking me. I read what I wanted to read. I'm sorry. But if you want to talk about that at some point outside of class, we can do so if you want to come by for office hours. That way you would have to have eclipsed drawings. No wonder why you were confused. And you could do them for twist conformations too. We're also not doing those. Trying to come up with a better way I can do this. So the test part 6 is asking to convert to avoid that. Well, I mean, you can try it if you want to, but I'm not going to test you on it. You can't assume that every semester I'm going to cover the same exact thing, so. Can I model it? I didn't bring my model kit home with me, I'm sorry. Also, that one was a typo. There's no chiral carbon on that. I had to correct my class on that last year when I did it. I meant to put on pentane and I wrote propane instead. Should it be rewritten on the same side? On the same side of what? The R and the S should be at the very beginning of the name. That's correct, Duncan. You're spelling it funny. Chiral. Also in the book. You guys need to look at your book. A chiral carbon is any carbon that has 4 different groups associated with it. So it has to be sp3 hybridized, and it has to have 4 different things. That's about the simplest definition I can give for you. Jacinta, let me pull this back up and we can do some of what you're asking me. So, and this is where ChemSketch is really awesome because you can use it to, you know, give yourself examples of naming stuff. Oh, shit. Let me try that again. Now, you do need to give it perspective because the computer can't figure it out any more than anyone else can, right? You have to have a perspective drawing to do any kind of stereochemistry. There we go. So You always want to put down the number with the stereo designation, so whether it's R or S, you just stick it at the very beginning. I'm not sure if that's exactly what you meant. I don't know what you mean by rewritten on the same side. But that's where you would put it in that name. Next question. If you're talking about the mirror images, the enantiomers, I still don't understand the question. Give you guys a fun one here. Because it's probably how everybody always feels the night before an exam. Dying. It sounds like dying. Okay, sorry. Well, I guess we could have done dying too. That would make more sense. Drawing it out in a line to the side instead of going down. It doesn't matter how you do it. It's all the same thing. You can do it this way. You can do it the way we did it in class. It doesn't matter. As long as you have it where the straight lines are in a plane with each other, and then the dash line and the bold line are kind of on the same side, one pointing behind the other, you're fine. So another way of drawing that same exact molecule would be like that. Hydrogen. I might have just made the enantiomer. What did I do? R. Yeah, I just made the enantiomer, sorry. Oh, shit. Gonna fix that. We'll say that looks about right. Bond angles might be a little bit off. So, I mean, this would be the same molecule. It doesn't matter. And I can figure out either way. If you got it right, you get it right. Count off if we put an N in butane. For alkenes and alkynes, you keep the N in there. So if you think about if you do an alkane, alkyne, all of them have an N in them, right? And so those are kind of taken care of. And if you had a number, you would put it in right there before the functional group, like that. And if you had 2, you would put a diene. And then you put an A in there so that you have a vowel and a consonant next to each other instead of 2 vowels. Or instead of 2 consonants, sorry. But don't get that confused with the other functional groups. So if you have a alkane that has an alcohol, it would look like that. And you would put the number in. And so that would have the A in the end. You just take off the E at the end. Whereas on the alkanes, the alkenes, the alkynes, you're actually removing the A and E from the end and putting in that different name, that different suffix. And I usually take off 1/4 of a point, if you're curious, like if you're going to fail the test if you do that. The answer is no. Oops. I feel like I need to turn music on my computer while you guys are in between questions because it's probably very weird just sitting here staring at me not doing anything. So that's a good question, Duncan. It is how you have it, but it's not because it's alphabetically. It's because if you have a double bond or a triple bond, it's still part of the parent chain. And so you put it with the part of the parent chain, and then you put the suffix at the end that's the functional group. So same way if I had any other kind of suffix for carboxylic acids or alcohols or amines, you would definitely put the... I don't know what you're asking me, Andrew. But yeah, if it's part of the parent chain, you just put it with the parent chain. Double bonds and triple bonds are part of the parent chain. And then you would put on any kind of substituent that's not part of the parent chain. So alcohols, amines, carboxylic acids, anything like that. Fantastic. Andrew, what are you asking me about priority groups? So far we've only learned about the Kahn-Ingold-Prelog priority groups for determining RNS, which is not really what we're talking about right here. We will learn them though. I can teach them to you tomorrow afternoon if you want. We haven't gotten there yet. The alcohol would go on the end. Those priority groups or priority designations are not the same as the Kahn-Ingold-Prelog rules. They revolve around what is the most reactive functional groups and give those priority as the suffix instead of as a prefix. So we haven't done those yet, but an example would be if you have an alcohol and a carboxylic acid on something, you would name it as a hydroxy carboxylic acid instead of an all carboxylic acid, OL. But we haven't gotten there yet. Yeah, don't, I mean, you can learn other stuff if you want, but you don't have to right now. Hi, Onyx. Let me go grab some more water. You guys asked some questions. I'll be back. Out of the way. I also might have gotten Easter candy. I could bring you guys Easter candy tomorrow. My favorite holiday is Thanksgiving, but my favorite candy comes from Easter. Are there any other questions? I'll still be up answering questions through email if you guys have them tonight. Oh, cyclohex. I can sketch it in Chem Sketch, Duncan. Would you prefer the chair conformation or just cyclohexene? Where did you want the double bond? One ene, one amine? Is that what you're asking me? Is that what you're asking me? And did you want the chair confirm? Well, here. I'll do it both. So, cyclohexane with an amine on it would look like that. Cyclohexene, one amine, if you wanted to get really exotic, would look like that. So cyclohexene, one amine, hex one ene, one amine. So yeah, like that. And then if we wanted to do that as a chair conformation, which we can do, if I can pull up my template window real quick, I think it's faster. I might be wrong on that. They have all the bicyclics I could ever want, but I don't see any. Screw it, that's just taking too long. Okay, I'll just do it by hand. Alright, so I'm just arbitrarily picking wherever I want the double bond. Doesn't matter. And then, oh, that one's going to be hard. Because we kind of change. And without having a model kit to show you, you kind of change the angle a little bit. But I think that's fine. Does that answer your question? Glad to help. There you go. Ooh, I wonder if it'll come up with it right if I do it there. I think it should. Yeah! So it recognizes the chairs is what they should be. Alrighty. Well, it's been wonderful talking with you guys tonight. As I said, feel free to, if you have questions about certain things, like if you're working on a problem or something. None of you guys asked me about any of the Fisher projections that I put online, so if you're working on those tonight and you have any questions about them, feel free to email me. I go to bed around like 1 or 2, so since we don't have class till later, I just kind of shift my sleep schedule accordingly. So if you guys have any questions, you're more than welcome to get in touch with me, and I'll do my best to answer them. And if that's it, then I guess that's it. It's been wonderful talking with you. I'll see you guys in the morning.